In the middle of the 19th century, a weighted line slips down through the Atlantic while the deck above waits in near silence. The men handling it know only what their hands can feel: the wet drag of rope, the pull of gravity, the faint uncertainty of contact far below. Somewhere under the hull lies a landscape no one has seen, a darkness so complete that even its shape feels hypothetical. At that moment, the ocean is not yet a real world in the scientific imagination. It is a surface crossed by trade, var, and weather, with an unseen depth that remains almost absurdly out of reach. Place yourself there for a moment, on a damp wooden deck with salt drying on the rail and instruments still crude by modern standards. The planet appears familiar, yet most of it is concealed beneath a moving skin of water. No telescope can help. No mountain can be climbed for a better view. The deep offers no horizon, only delay. A sounding line returns with numbers, mud, broken shells, or nothing at all. And from those fragments, scientists are asked to imagine pressure, life, temperature, form, and motion in a place where human beings cannot survive long enough even to look around. What followed was not a smooth march of discovery, but a long sequence of guesses, corrections, failures, inventions, and reversals. Some naturalists believed the deep ocean must be nearly lifeless, too cold, too dark, too crushing for anything complex to endure. Others suspected it was stranger than those tidy conclusions allowed. Engineers searching for routes for telegraph cables helped drag science downward. Expedition ships began dredging and measuring. Instruments improved, then misled. New maps appeared. Creatures came up from depths where no one expected them. And later, when human beings finally descended far enough to see with their own eyes, the ocean still refused to become simple. So how did humans discover a world that could barely be touched, much less entered? And what does it mean that each time science thought it had defined the deep ocean, the deep answered with something quieter, larger, and more unsettling than expected? The rope is wet and heavy in the hands, and the ship rises and falls almost imperceptibly as the line slips downward into black water. A lantern burns somewhere behind you, spreading a dull yellow pool across the deck. But beyond that circle of light, there is only night, wind, and the quiet work of waiting. The men guiding the line cannot see where it is going. They can only feel its passage, hear the faint rasp as it runs out, and measure distance by marks and memory. The surface is familiar enough. It shines, it breaks, it carries ships from one coast to another. But what lies under that shifting skin is another matter. Beneath the hull, there may be mud, rock, cold, silence, life, or nothing the mind can picture with confidence. The line goes down and down, and as it disappears, certainty seems to go with it. This is how the deep ocean first begins to enter human knowledge, not as a map or a theory, but as an absence one tries to touch. On land, distance can be walked. A mountain can be climbed. A valley can be crossed, measured, drawn, and returned to. Even the sky, for all its remoteness, can be watched directly. The ocean below the surface offers no such privilege. It hides its interior under movement. It has no visible threshold where one world ends and another begins. The surface reflects moonlight, cloud, and mast, yet yields almost nothing about the weight beneath it. For most human purposes, that had long been enough. Sailors needed winds, shoals, coasts, currents, reefs, harbors, and stars. Merchants needed passages. States needed routes. The sea was known through travel across it, not through descent into it. That older knowledge was practical, rich, and often hard-won. But it remained overwhelmingly horizontal. There is something quietly astonishing in that fact. Human beings crossed oceans, linked continents, fought naval wars, and built economies on maritime movement long before they had any coherent sense of the largest environment on Earth. A globe makes the ocean look already understood, as if all that blue stood for one familiar thing spread evenly over the planet. Lived history was nothing like that. Coastal people knew nearby waters intimately. Pilots learned channels and shoals with a precision that could feel almost instinctive. Mariners studied the look of waves, the smell of approaching land, the movement of birds, the dangerous texture of ice. Yet beyond the lowest reach of ordinary sounding, the water below remained largely outside thought, as though the world had a hidden underside that human culture crossed every day without ever entering. That helps explain why the deep was so slow to become a scientific object. It did not present itself as a landscape. It offered no cliffs exposing strata, no forest to walk through, no fossil bed laid bare in sunlight. It could not be sampled without distortion, and even language faltered around it. Darkness, depth, and danger were ancient human themes. But symbolic depth is not the same thing as measured depth. For centuries, the abyss lived more comfortably in myth, religion, and imagination than in disciplined observation. It was a place of monsters, submerged kingdoms, punishment, or simple unknowability. Those images told people much about fear and wonder, but almost nothing about the physical reality below, near coasts and harbors. Practical sounding had long existed. The lead line was simple and, within limits, remarkably effective. A weighted lead, sometimes with tallow pressed into its hollow base to bring up a trace of the bottom, could tell a sailor how much water lay below and whether the seafloor there was mud, shell, gravel, or sand in shallow waters that mattered enormously. It could save a ship from grounding or help identify a familiar anchorage. It could also create one of the earliest tactile relationships between human beings and the hidden floor beneath the water. A line lowered from a moving vessel might return not only a number, but a crumb of another world. Even so, the method belonged to an older scale of knowing. It worked best where the bottom was near enough to be reached reliably, where the line could fall more or less straight, where current and drift did not turn measurement into guesswork, and where the purpose of sounding was navigation rather than discovery. Beyond those conditions, the method began to reveal its own fragility. In very deep water, the line itself became a problem. It carried weight, absorbed water, drifted with current, angled beneath the ship, stretched under strain, and took so long to descend that the vessel might shift before contact with the bottom could even be judged. Sometimes there was doubt about whether the bottom had been reached at all. Sometimes the line seemed to go on indefinitely. Sometimes it returned with so little evidence attached to it that the result felt almost insulting, as if the planet had been asked a question and answered with silence. A measured depth in those conditions was never just a fact. It was an argument between instrument, environment, and interpretation. That matters because the deep did not enter science as a visible thing waiting to be described. It entered as resistance. Ships could circle the world more easily than they could understand what lay beneath them. Natural history flourished in many directions through the 18th and early 19th centuries. Collections grew, taxonomies expanded, instruments improved, observers became more systematic, yet the deep ocean remained stubbornly unlike everything else that science had learned to handle so well. A botanist could walk among plants, a geologist could strike rock with a hammer, an astronomer could return to the same sky. The investigator of great depth had no equivalent intimacy. What existed below had to be inferred from delayed, partial contact. That mismatch between scale and access shaped the imagination in subtle ways. The ocean was vast, but its depths remained mentally compressed, as if everything below ordinary experience could be folded into a single dim category called beneath. There were coasts, then open sea, and then somewhere below that open sea there was bottom, the enormous column of water itself, and the structure below it remained largely undifferentiated. The deep was not yet a place with regions, climates, ecologies, or history. It was a remainder. That is why the first measurements mattered so much. Even when they were sparse, they did more than add numbers. They forced the mind to admit that a concealed physical world existed on a scale it had not seriously accommodated. One of the moments when that admission became harder to avoid came in the work of James Clark Ross. Ross is often remembered for polar exploration, for ships among ice at the edge of the world. But he also belongs to this early phase when the ocean's hidden depth began to harden into fact. In 1840, during his Antarctic expedition, he carried out a deep sounding that became famous for its sheer scale. The drama of it was not theatrical. It was procedural, patient, exhausting. A line was lowered. Time passed. More line went out. The bottom, when reached, seemed astonishingly remote. The sounding did not suddenly illuminate the ocean floor or reveal its shape in any rich sense, but it made something newly concrete. The water beneath the ship was not simply deep in the ordinary language of sailors. It was profoundly, almost disorientingly deep, enough to challenge intuition itself. There is a particular kind of shock that comes not from seeing an unknown thing, but from measuring it and realizing the imagination had been much too small. Ross's sounding belonged to that category. It stretched the mind. If the ocean could be that deep in one place, what else might be hidden beneath water ships had crossed for centuries? How varied was the terrain below? Was it flat or broken? Barren or inhabited? Warm in places or cold everywhere? The sounding did not answer those questions. It enlarged them. Discovery often begins that way, not with explanation, but with the moment an old vagueness turns into a problem too real to ignore. Still, a few dramatic measurements do not create a science. For the deep ocean to become more than scattered astonishment, it had to enter a new kind of attention. That transition was slow. The practical world still rewarded surface knowledge first. Storms, coastlines, currents, and navigational hazards were urgent in a way the abyss was not. Most human life unfolded above the waterline, and most danger at sea did too. A captain could spend an entire career without needing a philosophical view of the seafloor thousands of fathoms below. The deep remained, in that sense, an expensive question. To investigate it required time, labor, specialized equipment, and a willingness to accept fragmentary results. And yet the pull of the question had already begun. Part of it was intellectual. There is a natural unease in realizing that the world one inhabits is materially larger than the world one understands. But there was also something more intimate at work. The deep, challenged habits of perception human beings had carried for ages. We trust what can be revisited, seen again, approached from another angle. We build confidence through repetition and proximity. The deep denied all of that. It demanded trust in instruments, in delayed traces, in evidence that arrived damaged and incomplete. Before anyone could map the abyss, they had to accept that the world includes realms that become real to us only through mediated contact. That gave the earliest deep ocean knowledge a peculiar emotional tone. The method was intimate. The object was remote. A scientist or sailor handled rope, lead, mud, and water with the hands. The act itself was close, repetitive, almost humble. But what those acts referred to was vast and unseen. The first approach to the deep was not a triumphant plunge into the unknown. It was a series of modest gestures, repeated against enormous scale. Lower the line. Wait. Recover the lead. Inspect the tallow. Record the depth. Compare one point to another. From such small motions, an entirely hidden part of Earth would slowly begin to take form. As the 19th century moved forward, those acts began to acquire new meaning. Better instruments would come. Arguments about life below would grow sharper. The floor beneath the water would slowly cease to be an abstract underside and start to look like a realm with character. But in this first stage, the governing feeling is still threshold. Humans had not yet discovered the deep ocean in any full sense. They had only begun to realize that the familiar surface world was resting on a hidden immensity. The sea was no longer just the road between lands. It was a lid over another Earth. Curiosity alone, though, rarely turns an unknown into a sustained scientific enterprise. Wonder can open the question. Other forces usually decide whether the question will be pursued with money, ships, improved technique, and institutional will. The deep ocean was about to be drawn into precisely that wider urgency. As cables, trade, naval power, an empire reached farther across the surface. The hidden floor below would begin to matter in a new and practical way. The rope descending into darkness would no longer belong only to isolated moments of inquiry. It would become part of a larger effort to connect continents and make the unseen world below answer to human use. And so, the line that had once descended, mostly in the service of curiosity, began to descend for another reason. It was still wet hemp slipping through human hands. Still a weight disappearing into water no one could see through. Still a patient and imperfect act of contact. But the question pressing down with it had changed. The hidden terrain below the waves was no longer merely a source of wonder or a blank remainder at the edge of knowledge. It was becoming an obstacle, a route, a possible support for human ambition. The darkness below had entered the path of commerce. By the middle of the 19th century, time itself was beginning to change shape. Messages that had once moved no faster than horses and ships were starting to travel at the speed of electricity. Telegraph lines spread across land with startling consequences. A government could know sooner. A market could react sooner. News could become current rather than delayed. Distance, which had governed human affairs for so long with almost geological authority, began to feel negotiable. Once that transformation started, the water between continents no longer seemed like a permanent interruption in communication. It looked like the next great gap to be bridged. That ambition gave the Atlantic a new kind of significance. It had long been a road of trade, migration, var, and empire. Now it was also imagined as a space through which information might pass continuously, invisibly, almost instantaneously. To dream of a cable from North America to Europe was to dream of more than engineering success. Governments would not wait weeks for dispatches. Financial centers would not remain at the mercy of delay. Imperial systems, commercial networks, and military command could all be tightened by the same wire. Beneath all of that desire lay a newly urgent question. What kind of ground actually existed under the Atlantic? And could it receive a cable at all? This was one of the quiet turning points in the history of knowledge. The hidden underwater landscape had been hard to study when it was merely unknown. It became harder to ignore when it stood in the way of a profitable and politically transformative project. In that sense, the first great advances in understanding very deep water did not come from detached contemplation alone. They emerged because the modern world had begun to demand a path through darkness. Engineers needed to know depths, gradients, sediments, and the broad character of the bottom. Investors wanted confidence. States wanted speed. The question was no longer simply how deep the water might be in some remote place. It was whether the world below could be made to serve the systems above. Few figures embody this change more clearly than Matthew Fontaine Maury. Maury had entered the United States Navy as a young man and spent years at sea before injury curtailed his active service. Forced away from shipboard life, he became something else, and in some ways something more historically consequential, a compiler of maritime knowledge on a scale few had attempted. At the Misled Naval Observatory, he gathered ship logs, weather records, current observations, winds, temperatures, and sounding data, trying to turn scattered experiences into patterns. He is often remembered as a pioneer of physical oceanography and of systematic navigational data, though his career also belonged to a world shaped by slavery, empire, and state power. Maury did not discover the Atlantic depths alone, but he had the kind of mind that sensed order in a mass of partial reports. There is something psychologically revealing about that work. Maury belonged to a 19th century type that could no longer rely on solitary encounter with nature. The scale had become too large, so he worked through accumulation, comparison, and the disciplined belief that patterns would emerge if enough records were gathered patiently enough. He read the movements of ships as a naturalist might read tracks in soil. Winds and currents became mappable. Routes could be optimized. Time at sea could be reduced. In that desk-bound labor, done far from storms and decks, the global ocean began to take on a new form as a system rather than a mere expanse. But data alone was not enough. The Atlantic still needed to be sounded more effectively if it was to be crossed by cable. The old lead line had severe limitations in very deep water. And one of the men who helped address this problem was Lieutenant John Mercer Brooke of the U.S. Navy. Brooke devised an improved sounding apparatus in which a heavy weight carried the line downward, but detached after bottom contact, allowing a lighter tube to be recovered with sediment from the seafloor. The principle was simple, almost elegant, though the conditions in which it operated were not. Its importance lay in what it made possible. Very deep soundings became more practical and more informative. The apparatus did not merely tell investigators how far down the bottom lay. It could also bring back a trace of what that bottom was made of. That small gain changed the quality of the question. A depth measurement is one kind of fact. A depth plus a sample is another. Once the returning device carried back ooze, shells, or fine sediment, the hidden ground became less abstract. The Atlantic was beginning to answer in material terms. It was not merely there. It had texture, composition, and local character. A cable enterprise did not need a romantic picture of the bottom, but it did need to know whether the route below was likely to be jagged, steep, unstable, or comparatively gentle. Out of Brooks' soundings and Maury's synthesis emerged the increasingly persuasive notion that parts of the North Atlantic contained a broad, relatively level region suitable for the laying of a telegraph cable. Maury spoke of a kind of telegraphic plateau, and the phrase mattered because it translated incomplete scientific knowledge into a usable vision. Here, at last, was not only an unknown depth, but a possible corridor. The seafloor was beginning to be imagined as terrain with economic and political potential. That is a profound conceptual shift. A place almost entirely absent from human experience was being turned into a planning surface. Charts and sounding compilations did not make the hidden world visible in the ordinary sense, but they made it newly thinkable. Investors and engineers could begin to imagine a cable resting across a broad submarine plain, carrying the impulses of modern states and markets through cold water between continents. Cyrus Westfield, one of the central promoters of the Atlantic Cable, drew on this emerging body of sounding knowledge in pressing the project forward. Here again, it is worth noticing the mixture of imagination and evidence. No one had seen the route in the way a modern survey team might later see it. Confidence was built out of charts, calculations, recovered sediments, scattered soundings, and the persuasive power of a diagram. The Atlantic, from the perspective of the cable dream, was transformed into something between a mapped reality and an informed wager. That blend of science, risk, and enterprise would define much of early deep water knowledge. The unseen zone first became legible where powerful reasons existed to make it legible. This appetite for underwater knowledge did not belong only to one nation. The mid-19th century was an age of expanding state capacity, imperial competition, shipping networks, and technical systems that increasingly reached across the globe. Hydrography, naval surveying, and marine measurement all took on greater strategic value. Coasts had always mattered to power, but now the spaces between coasts mattered in new ways too. It was no longer enough to know where harbors were and how currents ran near land. The undersea route itself, far from shore, had become a matter of calculation. In that respect, the movement downward into the Atlantic was part of a larger shift in how industrial societies treated nature. The world was not only observed and described, it was increasingly measured in order to be used, connected, and administered. Even so, the story was never as clean as the confidence of promoters sometimes implied. Early cable ventures were plagued by technical and financial difficulty. Insulation failed, signals weakened, cables snapped, ships struggled, storms interfered, and the strain of laying long lengths of heavy wire into deep water exposed how much remained uncertain. The great Atlantic cable projects of the 1850s produced both exhilaration and disappointment. In 1858, after enormous effort, an early cable briefly connected Europe and North America, only to fail after a matter of weeks. Even that short-lived success seemed extraordinary at the time, provoking celebration in the sense that a new age had opened. When the line died, what remained was not simply embarrassment. It was a harder understanding of how unforgiving the underwater environment could be. That pattern would recur throughout the history of deep-water discovery. Human beings were drawn below by tangled motives, and the environment answered each ambition with new complexity. The cable project drove sounding, charting, and bottom sampling forward, but it also revealed how little a few measurements could guarantee. A route that looked smooth in principle did not make laying and maintaining a cable easy in practice. The Atlantic was not just a geometric distance between coasts. It was pressure, cold, current, abrasion, electrical challenge, and logistical strain spread across thousands of miles. In attempting to unite continents, people discovered that the underwater world was not a passive backdrop waiting to be crossed. It had conditions of its own, and those conditions had to be learned slowly. At the same time, something important was changing in the human imagination. The water between continents was ceasing to be a blank transit space. Charts of winds and currents had already begun to reveal order in what once seemed fluid and wayward. Now sounding profiles and bottom samples added another layer. The Atlantic acquired depth not only in the literal sense, but in thought. There were basins, rises, softer sediments, harder obstacles, shallower banks, and routes that appeared more or less favorable once information began to accumulate. The world beneath the ship was no longer merely a mystery below navigation. It was a structured domain with features that could influence history above it. That changed the intellectual atmosphere in a subtle but lasting way. A hidden place that matters economically is rarely allowed to remain philosophically vague for long. Once capital, strategy, and communication depend on some fragment of nature, inquiry grows more precise. Better instruments are funded. Observations are compared more urgently. Reports that might once have remained scattered begin to be centralized and analyzed. This does not make the science less real. It simply reminds us that knowledge often advances where desire, pressure, and curiosity overlap. The Atlantic Cable era did not discover the underwater world out of innocence. It pulled on the depths because the modern world wanted connection. Maury's charts and Brooks' soundings therefore belong to more than the technical prehistory of telecommunications. They belong to the moment when the bottom of the Atlantic first entered sustained strategic thought. They helped establish the idea that the unseen geography below could be inferred, compared, and put to use. That may sound obvious now. After generations of bathymetric maps and submarine surveys, but at the time, it represented a serious enlargement of the known Earth. A person looking at a globe in the early 19th century saw great blue spaces that were effectively surfaces. By the time cable projects gathered force, those same spaces had begun to acquire hidden structure. Under the routes of ships, there was not just water and then bottom. There was a measurable underworld whose character could shape human plans. This is also why the story cannot be told as pure science detached from power. Telegraphy compressed time for governments, businesses, newspapers, and military planners alike. Faster communication meant faster coordination, quicker reaction, tighter control. Undersea cables would become the nervous system of an interconnected world, with all the ambitions and asymmetries that implied. The search for routes across the Atlantic was therefore never only a chapter in engineering. It was part of the wider history of how industrial empires tried to knit distant spaces into a single operational field. And yet, for all that pressure from above, the place below still resisted full comprehension. A sounding line could return a number and a sample, but it could not tell the whole story of the environment it touched. It could not reveal what forms of life, if any, inhabited those depths. It could not show how conditions changed with increasing pressure, diminishing light, or near-freezing water. It could not answer whether those sediments lay in stillness, or whether something moved there that human observers had barely begun to suspect. The cable age pulled inquiry downward for practical reasons, but in doing so, it widened a second and more unsettling question. If the Atlantic floor was real enough to bear a human wire, what sort of world surrounded that wire? That question began to hover more insistently as more material came up from below. Sediments, shells, and fragments complicated the older assumption that the great depths were merely empty remoteness. At first, the evidence was intermittent and open to interpretation. A few traces do not settle the character of an entire realm, but they disturb easy conclusions. The more carefully people sounded and sampled, the harder it became to treat very deep water as a simple void beneath the meaningful world of ships and nations, even commerce. In trying to turn the North Atlantic into an infrastructure corridor, had begun to stir another curiosity. The hidden ground was not just a support for cables. It was a place with physical and perhaps biological realities of its own. That is where the story turns from route to habitat. The cable dream had sought to master distance, but it also drew scientific attention into an environment that would soon refuse to remain subordinate to human plans. If pressure increased without mercy, if cold intensified, if sunlight vanished altogether, what then? Was there a depth beyond which living things simply could not continue? Or had the line and the dredge only brushed the edge of a richer story still waiting below? And so the question shifted again. Once people had begun to imagine the Atlantic beneath the routes of ships as a place with shape and sediment, another uncertainty rose beside it. If a cable could lie across that hidden ground, then what kind of environment surrounded it? What filled the long dark between surface light and bottom ooze? Did anything live there at all? Or did increasing depth carry the living world toward a final limit, beyond which pressure, cold, and darkness made existence impossible? To many thoughtful naturalists in the middle decades of the 19th century, that second possibility seemed entirely reasonable. It is easy now to treat the idea as quaint, because modern knowledge makes the answer look obvious in retrospect. At the time, however, almost every available intuition pointed the other way. Light faded with depth. Temperature seemed to fall. Pressure increased relentlessly. Plants, as far as anyone knew, required sunlight, and visible marine abundance appeared greatest near shore or near the surface, where warmth and light were still present in some form. Far below, there was only cold, darkness, and distance so absolute that it invited a clean conclusion. Perhaps life thinned out as one descended, and then stopped. That conclusion acquired one of its most famous formulations through Edward Forbes. Forbes was not a crank speaking from outside the scientific world. He was a talented and respected British naturalist, trained in medicine, gifted in zoology, and active in an age when the classification of living things still carried the excitement of a world being inventoried. He had a quick, synthetic mind, a taste for pattern, and a tendency, common among gifted thinkers, to reach boldly from partial evidence toward larger schemes. In some scientific lives, that temperament leads to insight. In others, It leads to conclusions later evidence cannot support. Sometimes it does both. Forbes had studied marine life through dredging work in the Aegean. And from those observations, he developed a picture of distribution organized by depth. Species seemed to change as the dredge descended. Some forms disappeared. Diversity appeared to diminish. The farther one moved from the sunlit upper waters, the more austere the environment seemed. In 1843, Forbes proposed that below about 300 fathoms there existed an azoic zone, a depth at which animal life would no longer be found. The word carried a severe clarity. Azoic meant without life. It suggested a boundary as clean as a line on a chart, a transition from inhabited nature to sterile condition. There was a certain elegance to the idea, and elegance can be persuasive. 19th century science often valued broad organizing patterns, especially when they transformed scattered observations into something resembling law. Forbes had already described depth zones in ways that felt systematic and almost terrestrial, as though the marine world, like a mountain, could be divided into belts of life according to changing conditions. Extending that logic downward toward a final zone of absence had a satisfying symmetry. It turned uncertain soundings, patchy dredgings, and environmental inference into a coherent picture. One can still feel the appeal of it. It made the hidden waters legible, and there was more than intellectual neatness behind it. The evidence available really did encourage caution. Dredging in those years was difficult, inconsistent, and often deceptive. A net or dredge pulled upward through long stretches of water could lose material, miss living organisms, or return with specimens damaged beyond easy interpretation. Bottom samples could be sparse. Absence of evidence was perilously easy to confuse with evidence of absence. Yet that danger was not always obvious from inside the work. If a naturalist repeatedly sampled deeper levels and brought back fewer organisms, the trend seemed meaningful. History of science is full of moments when the most dangerous results are not wild anomalies, but orderly patterns extracted from data too thin to bear the weight placed on them. The azoic hypothesis, then, was not a random mistake. It was an attempt to reason responsibly from the world as it appeared through the methods of the time. That is part of what makes it important. It shows how scientific error can arise not from indifference to evidence, but from genuine seriousness under conditions of uncertainty. Forbes had seen enough to believe there was order in marine depth. He extended that order into a terminal zone. Others found the logic compelling because it harmonized with their expectations about light, temperature, and pressure. The dark below seemed inhospitable, and the specimens reaching the deck did not strongly contradict that impression. A boundary to life felt intellectually natural. This is also where the psychology of scientific imagination becomes especially revealing. Human beings almost always use familiar experience to think into unfamiliar environments. In the case of very deep water, the mind reached first for deprivation. No light meant no plants, or at least none in the ordinary sense. No plants suggested no broad base for animal life. Great pressure seemed mechanically hostile. Cold suggested stillness and scarcity. Even the word depth carried an emotional tone of descent away from vitality. None of this was foolish. It was the mind trying, with limited guidance, to extend the logic of ordinary life into a place it could barely sample. The trouble was that nature is often least predictable where intuition feels most certain. Forbes remains compelling because he was both perceptive and limited in recognizably human ways. He was energetic, ambitious, intellectually restless, and capable of large conceptual framing. He lectured, classified, observed, and wrote with unusual speed. But quickness of mind can also intensify attachment to a good-looking theory. A pattern once seen begins to attract confirming evidence. Contradictory fragments are easier to treat as anomaly or error. Historians return to figures like Forbes because they show that scientific authority is not built only on correct answers. It is also built on style, reputation, plausibility, and timing. The Azoic hypothesis did not circulate merely because it existed. It circulated because it came from a respected investigator offering a coherent picture, at a moment when coherent pictures were badly wanted. Behind this stood a broader 19th century habit of thought, the belief that nature arranged itself in gradients, zones, and natural limits. This was an era fascinated by distribution. Botanists traced vegetation by climate and altitude. Geologists thought in layers and epochs. Naturalists described faunal regions. To suggest that marine life also followed a downward series toward extinction fit neatly with that appetite for patterned worlds. The unseen waters could thus be made to resemble other environments already brought into conceptual order. They could be zoned, disciplined, made less alien, even while the hypothesis spread, though it carried a quiet fragility. Much depended on the quality of dredging, the interpretation of sparse catches, and the leap from local observation to a global claim, the Mediterranean, where Forbes had done much of the work shaping his view, was not the whole planet. Its conditions did not necessarily stand for all marine environments. Different currents, temperatures, and depths elsewhere might complicate the picture. More quietly still, there was an epistemic difficulty that would recur again and again in underwater science, when investigating a place almost inaccessible to the senses. How much confidence should be granted to clean theories built from imperfect retrievals? The tidier the theory, sometimes the more one should worry. Contrary signs began to appear. Naturalists and surveyors working in other waters occasionally recovered organisms from greater depths than the proposed boundary seemed to allow. Such evidence was often fragmentary, open to dispute, or dismissed as unreliable. Some specimens might have been snagged while the dredge moved upward, rather than at the bottom. Others might have been misidentified or badly preserved. These objections were not always unreasonable. In a field where method was still unstable, skepticism about surprising claims was part of honest practice. But the pattern is worth noting. A strong theory had taken shape early, and the evidence required to loosen it had to be both repeated and difficult to explain away. One of the important figures in this slow unsettling was Louis-François de Pourtalès, a Swiss-born naturalist working with the United States Coast Survey. In the waters off Florida, de Pourtalès conducted dredging that yielded signs of life from substantial depths. Here again, the history is not a neat tale of one decisive contradiction arriving to destroy a mistaken doctrine overnight. His results accumulated within a world still learning how to trust its own underwater methods. Field conditions were demanding. Interpretation remained cautious. Even when living forms turned up below where Forbes's line suggested they should not, broad scientific opinion did not instantly reverse itself. Still, the pressure on the old idea was growing. Each recovered specimen from greater depth forced an awkward choice. Either the methods were misleading in ways that conveniently preserved the theory, or the theory itself was too rigid for the environment it claimed to describe. What makes this period so rich is that the argument unfolded in a zone where observation, technology, and imagination were all under strain at once. No one could simply descend and inspect the matter directly. Evidence had to be lifted, sorted, compared, doubted, and weighed against expectations formed in near total darkness. The dispute was therefore also a dispute about what kind of indirect evidence deserved belief. There is a quiet irony here. The same century that was becoming more confident in its instruments was learning, in underwater work, just how indirect knowledge can magnify uncertainty. A dredge might return empty because nothing lived at that depth. It might also return empty because it had skipped, torn, clogged, or failed to catch what was there. A few shells or delicate organisms might survive retrieval from great depth, but they might arrive broken or incomplete. In many fields, such obstacles would have been unusual. Here they were structural. The environment being studied distorted the very process of acquiring evidence from it. So the azoic hypothesis did more than make a claim about marine life. It exposed a larger difficulty in the scientific encounter with very deep water. How should one reason when every sample is partial, every retrieval is violent, and direct observation is absent? A satisfying answer had not yet been found. In that gap, theory rushed ahead of method. Forbes's boundary offered intellectual stability. It gave the hidden waters an order one could picture. But each contrary sample whispered that the picture might be simpler than the place itself. The debate had implications beyond zoology. If life truly vanished below a certain depth, then the planet's largest environment contained a vast sterile region. The emotional effect of that idea was considerable, even when expressed in calm scientific language. It suggested an underwater desert of immense scale, a realm beneath the ordinary living Earth, where physical conditions overruled biology entirely. Such a picture reinforced the sense of great depth as an almost planetary elsewhere, separated from the warmer, brighter, inhabited world above by more than distance. It turned depth into a kind of natural exile. For a time, that image held textbooks, lectures, and summaries repeated it. The authority of Forbes's name helped. But so did the fact that the claim felt like common sense elevated into science. When a theory agrees with both limited evidence and prevailing intuition, it can become surprisingly stable. One must remember, too, that the mid-19th century did not yet possess the massive coordinated expeditions, global sampling programs, and more disciplined marine methods that would later reshape the field. Evidence remained scattered among voyages, surveys, and regional studies. There was still too much darkness between one data point and the next. Yet science often advances through exactly that discomfort. When a pleasing generalization begins to encounter stubborn facts that refuse to fit, some of the most important changes in understanding begin not with a grand new theory, but with a series of small embarrassments. A specimen from an unexpected depth, a shell where none should be, a dredge haul that refuses to cooperate with the map of nature already drawn. The old order can endure such anomalies for a while, especially when they are technically contestable. But once enough of them gather, something starts to shift. The theory survives only by becoming increasingly defensive. By the 1860s, that defensive posture was growing harder to maintain. Work in the North Atlantic and elsewhere was producing results that strained the azoic line. Michael Sars, among others, had already contributed to a growing unease by reporting life at depths greater than some older assumptions allowed. The point is not that one investigator alone overturned the view, but that a community of naturalists and surveyors was gradually being forced to confront a more complicated reality. Each additional trace from below increased the sense that the boundary might not be where Forbes had placed it, or might not exist in the absolute way he had imagined. What remained missing was scale. A few surprising catches could disturb a theory, but they could not easily replace it with a richer account of the underwater world. To move beyond the argument over a single boundary, science needed something more systematic than scattered contradiction. It needed a voyage designed not merely to support commerce, and not merely to settle one dispute, but to investigate the underwater realm as a domain in its own right. It needed repeated soundings, repeated dredgings, repeated temperature measurements, repeated collections from many latitudes and depths. It needed organization equal to the magnitude of the question. That is why the Azoic hypothesis deserves to linger in the mind. It marks the moment when the hidden waters first became a serious intellectual battleground. The issue was never only whether Forbes had drawn the line too low or too high. It was whether humanity was capable, with the methods then available, of making strong claims about a place so resistant to ordinary evidence. The debate revealed the seduction of neat conclusions, the burden of indirect observation, and the vulnerability of even thoughtful science to environments that exceed its reach. Soon, a new kind of expedition would begin to alter that balance. The scattered samples, disputed dredges, and elegant but uncertain limits of mid-century natural history were about to meet something larger, more deliberate, and more ambitious. The question of whether life existed in the great darkness below would not vanish at once, but it would be drawn into a scale of inquiry broad enough to transform the very study of the waters themselves. That larger inquiry began, fittingly, with a ship. When HMS Challenger left Portsmouth in December 1872, it carried with it something more ambitious than a voyage of collection or a sequence of useful measurements. It carried a new scientific posture toward the waters of the world. The vessel itself had once been a Royal Navy corvette, built for service in a different spirit, but it was refitted for research, stripped of much of its military equipment, and turned into a floating laboratory. The transformation was symbolic as well as practical. A ship designed for power and movement through imperial space was being adapted for patience, observation, and repeated contact with places no one could see directly. In that conversion, one can feel a quiet shift in the 19th century. The planet was no longer only to be crossed, defended, or exploited. It was also to be studied at the scale of its hidden immensities. At the scientific center of the expedition stood Charles Wyville Thomson, a Scottish naturalist whose interests had already brought him close to the question of life in very deep water. Thomson had participated in earlier dredging work in the North Atlantic, including expeditions aboard Lightning and Porcupine, and those experiences had helped convince him that the old Azoic certainty could not stand. He was not alone in that conclusion, but he had the temperament to see that what was needed next was something far larger than another isolated contradiction. He wanted a voyage systematic enough to turn fragments into a field. If the great darkness below was not dead, then what exactly was it? The answer could not come from one dredge haul or one persuasive lecture. It required repeated soundings across many latitudes, trawls from many depths, thermometric measurements, sediment sampling, current observations, chemical analyses, and a willingness to spend years at sea gathering data from environments that would remain invisible even while being studied. The Challenger expedition was designed for that magnitude of effort. During nearly 4 years of travel, it crossed the Atlantic, worked through the Southern Hemisphere, moved across the Indian Ocean, passed through the Pacific, and returned with a volume of observations no earlier enterprise had attempted in such a coordinated way. By the time it ended in 1876, the ship had traveled tens of thousands of nautical miles, taken hundreds of deep soundings, performed numerous dredges and trawls, and collected specimens and measurements from an enormous range of locations. From a modern distance, it is tempting to compress all of that into a neat phrase and say that Challenger founded oceanography. There is truth in that. But the phrase risks smoothing away the texture of what it meant on board. Scientific work at sea was laborious, repetitive, physically awkward, and deeply dependent on weather, equipment, and routine. A sounding in deep water was still an event of time and tension. Nets and dredges had to be lowered and recovered with care. Specimens arrived damaged, entangled, or coated in mud. Temperature measurements demanded painstaking handling. The ship itself was always in motion, however slight. Every result had to be coaxed upward from an environment that still could not be entered. That alone makes the voyage more interesting than a triumphal summary suggests. Challenger did not abolish the old difficulty of knowing through indirect contact. It multiplied the attempts, standardized them, and extended them across the globe. A scattered world of isolated data points began. Slowly. To acquire density, depth was no longer simply a vertical number. It became linked to temperature, sediment, organism, and location. The ground below was not an abstract underside. It showed differences. The column of water above it showed differences too. The expedition's measurements helped reinforce the growing recognition that vast regions below the surface were remarkably cold, and they gave that cold a more systematic reality. This broadening from single questions to a whole interlocking field is one of the most important things Challenger accomplished. Earlier debates had often been framed around whether life could exist past a certain depth. The expedition did gather evidence bearing on that issue, and it helped bury the older confidence with which lifelessness had once been proposed. But as the work progressed, the scope widened. There were forms of animals to describe, distributions to compare, sediments to classify, temperatures to chart, currents to infer, and depths to record in relation to one another. A hidden region of Earth was ceasing to be merely the site of an argument. It was becoming an object of organized knowledge. The ship's naturalists and crew were therefore engaged in a more radical act than even they may have felt from day to day. By lowering lines, dredges, trawls, and thermometers again and again, they were helping convert the underwater realm from philosophical obscurity into a research domain with its own methods, materials, and expectations. Scientific fields do not arise simply because interesting questions exist. They arise when enough procedures, tools, records, and communities are built around those questions that the unknown begins to yield comparable results. Challenger provided that scaffolding. At the same time, the voyage retained something deeply old-fashioned in its sensory reality. One can picture the deck at odd hours, the slow hauling of gear, the smell of rope, salt, and preserved specimens, the cramped labor of sorting unfamiliar organisms that had arrived from unimaginable depths only to meet human hands under lantern light. There is a strange intimacy in that image. These were creatures and sediments from places no eye had seen alive or in place. The world below still could not present itself directly. It arrived as fragments on a deck. Yet those fragments were now arriving in enough quantity, from enough places, that the imagination had less room to impose a simple order of its own. Nature was beginning to answer more insistently, even if still through damaged and displaced evidence. Thompson is an especially interesting guide through this moment because he seems to stand between two scientific styles. On one side, there was the older naturalist's delight in collection, description, and the ordering of forms. On the other, there was the more system-oriented discipline that would later define oceanography more fully, with its attention to physical processes, global patterns, and interrelated measurements. Thompson belonged to both worlds. He cared about living forms, but he also recognized that the lower waters could not be understood by zoology alone. The expedition's results required a broader frame. In that sense, the invention of the deep sea as a scientific reality was also the invention of a new way of combining disciplines that had previously been more separate. The publication of the results would make this even clearer. The expedition did not end when the ship returned. In some respects, its most lasting influence began then. The reports generated from Challenger filled 50 large volumes over the years that followed, a monumental editorial and analytical labor turning shipboard observations into a durable body of scientific literature. John Murray, who had sailed on the expedition as one of its naturalists, played a central role in bringing that project to completion, especially after Thompson's health declined and he later died in 1882. Murray is sometimes overshadowed by the romance of the voyage itself, but his importance is immense. Discovery at this scale required not only a voyage of measurement, but a second voyage of organization, writing, classification, and interpretation. There is something revealing in that. The underwater world did not become scientifically real at the moment it was touched by a dredge. It became real through an entire chain of labor, extending from sampling to preservation, to comparison to print. The ship, the specimen jar, the notebook, the table of temperatures, the lithograph, the taxonomic description, the bound report, all were part of the same long act of making a hidden realm intellectually inhabitable. Knowledge of inaccessible places is always collaborative in this way, even when later memory prefers a few famous names. Challenger is best understood not as a single heroic insight, but as a machine for producing disciplined encounter. And what it encountered was abundance. Not abundance in the easy surface sense of teeming shoals visible in clear water, but abundance in the more arresting sense that the lower waters and sediments were full of forms, traces, deposits, and variation that no brief summary could contain. Thousands of species would eventually be described from the collections. Some were entirely new to science. Others complicated existing classifications. Sediments revealed broad patterns in the composition of the seafloor, including now famous categories such as Globigerina ooze, Radiolarian ooze, diatomos, and red clay, each associated with different conditions and regions. These deposits were not merely inert labels. They suggested that the world beneath the waves had geography, chemistry, and history of its own. That recognition had a philosophical force beyond the immediate findings. It meant that the largest environment on Earth was not an empty interval between continents, nor a featureless receptacle under the routes of ships. It had internal variety. It had its own sediments, its own thermal conditions, its own communities of life, and eventually, one would suspect, its own hidden topographies on a scale not yet fully grasped. The lower waters were becoming a world with character. That word matters. Character is what a place acquires when it can no longer be reduced to a single idea. For the old Azoic view, this was deeply corrosive. It was not simply that some animals had now been recovered from greater depths. That had already begun to trouble the theory before Challenger. The expedition made the trouble systemic. Repetition across many stations and many environments created a cumulative argument that was harder to dismiss as accident or methodological confusion. Life was not a rare intrusion into an otherwise sterile realm. The lower waters and their bottom environments were part of the living earth, sparse in some places, strange in many. Difficult to sample almost everywhere? Yes, but not dead. That shift may seem straightforward to modern ears, yet its emotional significance in the 19th century was considerable. A huge fraction of the planet had just moved. Intellectually, from presumed sterility toward inhabited complexity, the dark below the photic zone, once imagined as a nearly terminal region where physical hardship extinguished life, now had to be approached as a setting with its own biological reality. Human beings had not merely extended their map, they had revised their sense of where life belonged. If organisms could endure far below sunlight, under pressure and cold long treated as nearly prohibitive, then the limits of habitability were already less obvious than they had seemed. Even so, it would be a mistake to imagine that Challenger solved the underwater world in one sweep. The expedition transformed the scale and seriousness of inquiry, but it also exposed how much remained difficult to know. Samples were still disturbed by retrieval. Organisms were often known only in death. Behavior, color in life, movement through darkness, and the subtler relations between animal and environment largely escaped capture. Measurements themselves could be imperfect. In a quiet way, Challenger did something wonderfully scientific. It enlarged certainty in some areas while also enlarging awareness of how much could still go wrong. That balance is one reason the expedition retains such power. It stands as both foundation and reminder. Foundation, because it established marine research on a global, coordinated scale and helped bring a whole field into being. Reminder, because even the most celebrated investigations reach the unknown through imperfect means. The Great Voyage did not produce an immaculate picture. It produced something more valuable, a workable and expanding framework that others could revise, correct, and deepen. One can almost feel the atmosphere changing in its wake. Earlier, an investigator might ask whether anything at all existed beyond a proposed boundary of depth. After Challenger, the questions were richer. What species lived where, and under what conditions? How did temperatures vary? What were the sediments made of, and why did they differ? What was the shape of the lower terrain over long distances? How were currents, deposits, chemistry, and life intertwined? The hidden region had become generative. Instead of one defensive dispute, there was now a field full of open problems. By the late 19th century, the waters below ordinary sight had entered European and American science with a new weight. Textbooks changed. Museum collections expanded. Marine stations and national surveys inherited a stronger basis for comparison. Investigators could now speak of the great depths with more than speculation or occasional surprise. A shared reference point existed. Challenger had given the field a body of facts large enough to stabilize discussion without closing it. Yet stabilization brings its own temptations. Once an environment becomes scientifically real, the mind begins to crave coherence. Collections invite classification. Strange samples tempt overinterpretation. Patterns drawn from preserved material can look more complete than they really are. The very success of systematic sampling can encourage the illusion that what has been hauled upward is already enough to define the place it came from. In the years after Challenger, marine science would continue to grow in confidence. And with that confidence would come distortions of its own, errors born not of ignorance alone, but of abundance, method, and the wish to see unifying forms in incomplete evidence. The ship had made the great darkness legible in a new way. But legibility is not the same thing as transparency. Much still remained hidden, and some of what seemed newly clarified would soon prove less secure than it appeared. And in that gap between legibility and transparency, error found room to grow. Once enough specimens, sediments, and measurements had begun to accumulate, the lower waters could at last be studied as something more than rumor. But this did not mean they could be read cleanly. In some ways, the very success of large expeditions created a new vulnerability. The more material arrived on deck, the stronger the temptation to believe that the unseen place from which it came was already yielding its essential truth. Yet every sample had been torn upward through pressure change, shifting temperature, mechanical stress, and the simple violence of retrieval. Every jar, every net, every clump of ooze carried information, but also distortion. The underwater world was becoming scientifically real, and at the same time, it remained capable of deceiving the people trying hardest to know it. There is something almost inevitable about that stage in discovery. When a hidden environment first becomes accessible through tools, the tools often seem miraculous. They extend the senses. They produce evidence where there had once been only speculation. But instruments also shape what can be seen and what can be mistaken for seeing in late 19th century marine science. This was not a minor inconvenience at the edges of the field. It was part of the field's basic condition. The lower waters could not yet be observed directly. They had to be inferred from what arrived later, altered by the journey upward. Knowledge was being built through contact, but contact was always imperfect. One of the clearest examples concerns a substance that briefly seemed to promise an answer to one of the century's deepest questions. In the years after Darwin, European science was intensely interested in origins, primitive life, and the possible continuity between the simplest living matter and the more elaborate forms familiar on land and in shallow water. The great depths, newly yielding strange sediments and scarcely understood biological traces, seemed like a plausible place for primordial simplicity to endure. If the Earth's oldest or most elemental forms of life still existed somewhere, perhaps they might be found far below sunlight, in the cold and quiet where change appeared slow and the world seemed ancient. Into that atmosphere came Bathybius haeckelii. The name itself had a faintly mythic sound, half Greek depth and half learned taxonomy, as though the substance were already halfway to legend. Thomas Henry Huxley, one of the most influential scientific figures in Britain, examined a gelatinous material found in certain deep-sea ooze samples and described it as a primitive form of life. Huxley was no marginal enthusiast. He was a formidable anatomist, a gifted public intellectual, and one of the most important defenders of evolutionary thought in the English-speaking world. If someone like Huxley entertained the possibility that this strange slime represented living protoplasm spread across the lower reaches of the globe, the idea would naturally carry weight. And for a while, it did. Bathybius appeared to offer something almost irresistibly seductive. It seemed to bridge two desires at once. First, it gave the deep a new kind of biological significance. The lower world was not simply inhabited by scattered resilient creatures. It might hold an immense primitive living substrate, something close to the material threshold of life itself. second. It resonated with a period fascinated by protoplasm as the basic stuff of living organization. The thought that a nearly formless, gelatinous substance might occupy the sediments of the Atlantic or other great depths had a conceptual beauty to it. It allowed the underwater realm to seem both biologically active and philosophically fundamental. But Bathybius was not what it seemed. The substance turned out to be an artifact, largely produced by the interaction of alcohol preservatives with calcium sulfate in the sediment samples. What had appeared to be living matter was, in effect, a chemical illusion generated by method. The episode is worth dwelling on because it is so characteristic of the field's predicament. Scientists were not imagining things in the absence of evidence. They were confronting evidence that had been transformed by the means used to preserve and examine it. The false life of Bathybius was born in the space between collection and interpretation, where the hidden environment could still be altered into something it had never been. Huxley later acknowledged the error, and in that acknowledgement there is a kind of scientific dignity. Still, the mistake remains instructive precisely because it involved a mind so capable and so disciplined. Bathybius was not accepted because marine science was unserious. It was accepted because the culture of the time was primed to notice certain possibilities, because the material on hand seemed to support them, and because the environment under study could not be checked against direct observation. One cannot simply step down beside a jar of deep-sea ooze and ask whether its gelatinous veil is present in place. The underwater world was accessible enough to generate theories, but still inaccessible enough to delay their correction. This pattern extended far beyond one famous false organism. The whole practice of dredging and trawling from great depth was haunted by uncertainty. A net lowered far below and drawn back up could tear, collapse, drag at the wrong angle, or collect material not where one assumed it had been collected. Organisms might be crushed, fragmented, or tangled beyond easy recognition. Delicate bodies, especially gelatinous ones, could be destroyed almost entirely, leaving only hints that something soft and living had once been present. A sample might look barren because nothing had been caught, or because the most fragile inhabitants had not survived the ascent. The absence of life in a hull could never be read with perfect innocence. Even the mechanics of the work imposed their own forms of misdirection. Hempline, widely used in earlier sounding and dredging operations, absorbed water, became heavy, twisted under strain, and could break after long immersion. During expeditions in the 1870s, these difficulties were not theoretical. They could ruin a station's work entirely. The line might part after hours of effort, taking gear and sample with it. It might stretch or drift enough to confuse one's sense of where the instrument had actually touched. Investigators were often forced to work inside a compromise between what they hoped their apparatus was doing and what conditions at depth allowed it to do. The water column itself inserted ambiguity into every act of contact. This became painfully clear on expeditions that followed in the wake of Challenger. The American vessel Hassler, for example, undertook deep dredging work that ran straight into the physical limitations of older equipment. Long, wet lines could rot, foul, and fail. Gear intended to explore hidden terrain was often defeated by that terrain's sheer remoteness. From the perspective of grand scientific history, one might speak of the advance of marine research. From the deck, it often felt like repeated near failure. Hours of lowering, waiting, hauling, and adjusting might end in a broken line, and nothing to show for it but exhaustion and a clearer sense of the environment's resistance. And yet such failures were not sterile. They taught scientists and engineers what the water column was doing to their methods. They showed that new kinds of materials and new techniques were needed if the lower world was to be sampled more reliably. The transition from hemp to steel wire in later work mattered for exactly this reason. It was not only an engineering refinement, it altered the quality of the scientific relationship between humans and depth. Lighter, stronger wire made it easier to reach farther down, recover apparatus more consistently, and reduce some of the maddening uncertainties produced by older lines. A hidden region first entered science through fragile contact. Only later could that contact be made somewhat more disciplined. The vessel Blake, working for the United States Coast Survey in the 1870s and 1880s, belongs to this phase of improvement. Associated with men such as Alexander Agassiz and Charles Dwight Sigsbee, it helped refine deep water operations through better sounding and dredging practices, including steel cable and more advanced machinery for handling it. These changes may sound technical, but they transformed what sorts of questions could be asked with confidence. When methods break constantly, the scientist is trapped in doubt about whether the environment is resisting description or whether the instrument is simply failing. A more dependable system does not eliminate ambiguity, but it narrows the field of possible self-deception. Still, stronger gear solved only part of the difficulty. Even a perfect recovery would not restore the conditions under which an organism had lived. Pressure fell away during ascent. Temperature shifted. Motion altered fragile tissues. Creatures adapted to darkness arrived beneath bright human light, already dying or dead. Color could fade. Structure could collapse. Behavior vanished entirely. Marine science in this period therefore existed in a strange epistemic state. It was receiving more and more material from below, and yet much of the life of that material had already been lost by the time it could be studied. The place was yielding bodies, not scenes. It was yielding evidence of existence, not existence as experienced. That distinction matters more than it may first appear. A preserved specimen can answer certain questions magnificently. It can reveal anatomy, relationships, structural adaptation, and taxonomic placement. But it cannot fully reveal how an organism moved, how it floated or rested, how it responded to light, what posture it held in the water, or how it interacted with others nearby. In an environment already prone to projection, this invited a particular kind of overreach. Investigators could say with growing confidence that the lower realm was inhabited, but its style of life remained elusive. The unseen region was being described through its remains. Sometimes the uncertainty arose not from lost delicacy, but from abundance interpreted too quickly. Sediments, for example, could become intellectually dangerous in their own way. Once categories of ooze and clay were established, they encouraged broad thinking about deposition, environment, and global pattern. Much of that thinking was fruitful, yet classification can create a subtle illusion of completeness. A labeled sample seems to fix a place. It gives the mind something stable to hold. But the bottom from which a sample came was not merely its sediment. It was also microfauna, water movement, chemistry, burial, disturbance, and time. The sample invited the human tendency to reduce a living setting to the material that happened to survive extraction. The most interesting scientific mistakes often happen where desire for coherence meets an imperfect window onto reality. Bathybius is memorable because it was vivid, but the underlying habit was more general. Investigators wanted unifying pictures. They wanted to know what kind of world lay below. They wanted forms simple enough to communicate, compare, and publish. The lower waters, by contrast, kept arriving in pieces. A successful field of study had been born, but the field's object remained inaccessible enough to resist the neatness of the categories formed around it. This is why the history of marine science cannot be told as a simple triumph of better data over older ignorance. Better data did arrive. Methods improved. Entire false theories collapsed. Yet every gain in reach created new opportunities to be misled. The underwater realm responded to growing scientific attention by becoming richer, but also more complicated. Once the azoic picture had been weakened, researchers might have imagined they were passing into a more secure era. Instead, they found themselves in a landscape of partial truths: damaged organisms, clever apparatus, broken apparatus, persuasive artifacts, and an ever-present gap between the living place and the evidence dragged into air. There is a quiet lesson here about the psychology of discovery. Human beings do not simply fear the unknown. Very often, they long to resolve it into something intelligible as quickly as possible. A chart, a name, a specimen, a theory, even a false gelatinous primitive life can be emotionally satisfying because it relieves the strain of uncertainty. The hidden region below the surface produced that strain in unusual abundance. It offered too little direct inspection for comfort, but enough evidence to tempt explanation. In such settings, error can feel almost like rest. A mistaken answer is easier to live with than a place that remains structurally difficult to picture. And yet marine science was learning from exactly these humiliations. Each broken line taught something about the limitations of gear. Each dubious haul sharpened awareness of how retrieval could misrepresent the place of origin. Bathybius taught a harder lesson still. A sample altered by preservation could generate an entire theory if enthusiasm outran control. None of this made the field weaker. Over time, it made it more mature. It encouraged better technique, more skeptical comparison, and greater caution in drawing vast conclusions from isolated material. But even maturity could not solve the deeper problem, because the lower realm was still being approached indirectly. To know such a place more truly, one would have to do something earlier. Generations of naturalists could scarcely imagine in practical terms. One would have to stop relying only on what could be hauled upward and try, somehow, to see the environment where it was. Not simply its bones, shells, oozes, and torn soft bodies, but its living atmosphere. One would have to descend. By the early 20th century, scientists had learned a great deal about life below the sunlit surface. Yet they still knew it in a strangely incomplete way. They knew outlines without presence. They knew anatomy without motion. They knew the older image of sterile darkness had failed. Yet the replacement picture remained composed largely of specimens, instruments, and inference. The next step in understanding would require a different relation between observer and environment, one in which the human eye, however briefly and under extraordinary protection, entered the place that had so long been known only through delay and distortion. So the desire changed again. After decades of lines, dredges, jars, broken specimens, and beautifully organized uncertainty, the question was no longer only how to bring material up from below. It was how to stop losing so much of the place itself in the act of retrieval. If life far beneath the surface had already overturned older assumptions, then it had become increasingly unsatisfying to know that life only through bodies damaged on their way into air. Color vanished. Tissues collapsed. Movement disappeared. And whatever atmosphere belonged to that world was stripped away before a scientist could begin to describe it. At some point, the logic became hard to ignore. If one wanted to know the lower waters more truly, the observer would have to descend. Few people were better prepared for that shift than William Beebe. He was not simply a collector of facts or a manager of specimens. He was a naturalist with an unusually vivid sense that animals belonged, first of all, to their own living settings. Born in 1877, Beebe had already built a wide-ranging career long before he became associated with deep descents. He had worked with birds, tropical environments, and field expeditions. And he wrote with a fluency that made him more than a specialist, speaking only to other specialists. What runs through much of his work is a kind of impatience with lifeless knowledge, or perhaps a dissatisfaction with any science that stops at classification when the living scene has not yet been seen. He did not reject specimens. He knew their value well, but he felt, with increasing force, that to understand an organism, one had to encounter it in its own world, under its own conditions of light, movement, and relation. That instinct helps explain why Beebe became one of the central figures in the next transformation of underwater science. By the early 20th century, the waters below ordinary reach had become more populated in scientific thought, yet they were still strangely abstract. Naturalists knew that the old image of sterility had failed. They had descriptions, preserved forms, and a growing sense of vertical distribution. Even so, the environment itself remained curiously absent. The lower world had been reconstructed from remains and traces, not watched as an active setting. Beebe sensed that gap with unusual clarity. The challenge was no longer simply to prove that life existed below. It was to look at that life where it lived. The means for doing so came through Otis Barton, an engineer with a fascination for underwater descent. Barton was younger than Beebe, technically minded, imaginative, and willing to pursue a design that many would have considered outlandish. His proposal centered on a steel sphere, compact and brutally simple, because a sphere distributes external pressure more evenly than more complicated shapes. The chamber that emerged from this collaboration was small, thick-walled, and severe inside it. There was room for little more than 2 men. Essential equipment: oxygen supply, systems for absorbing carbon dioxide and moisture, a telephone line to the surface, and small windows of fused quartz through which the outside darkness might be seen. The vessel would not move through the water under its own power. It would be lowered from above, suspended by cable, like a deliberate answer to all the earlier ropes and sounding lines that had gone down blindly. There is something fitting in that continuity. The older history of lowering instruments into darkness had not been abandoned. It had been compressed into a new form. Instead of a lead weight or dredge descending into uncertainty, now there would be a human mind inside the apparatus. The bathysphere, as it came to be known, did not solve every problem of access. It was narrow in scope, localized, and dependent on surface support. But it altered the relationship between observer and environment in a way no trawl or jar ever could. For the first time, a scientist could remain inside the world he was studying while it was still that world, not a damaged shipment arriving afterward. Bermuda became the setting for these descents, and that choice mattered. The waters nearby dropped steeply enough to allow very great depths not far from shore. making repeated operations more feasible than they might have been in many other places. From a support vessel, the sphere could be lowered steadily, while those inside reported what they saw through the telephone line to colleagues above. The scene itself must have had an odd mixture of modern engineering and old maritime ritual. A heavy steel chamber swung over water, sealed with bolts, entrusted to cable and winch above, a ship and crew below, a darkness thickening as sunlight fell away. The descent was mechanical. The encounter it allowed was intimate. Imagine the experience for a moment, not romantically, but physically. The chamber is cramped. The walls are close. Air and light are carefully managed. There is no freedom of movement in any ordinary sense. No possibility of opening a hatch or adjusting one's surroundings. The observer is protected, but also contained. Outside the small windows, the water changes from lit blue to dim blue, then to shadow, then to black pierced by beams and intermittent life. The deeper the sphere goes, the more ordinary human bearings fall away. There is no horizon, no stable sense of up and down in the visual field, only the moving relation between the illuminated window and forms that appear briefly out of obscurity. That psychological threshold is part of why the bathysphere descents mattered so much. Beebe was not merely looking at animals from a different angle. He was entering a perceptual situation fundamentally unlike shipboard collecting. The older marine science of the lower world had been dominated by delay. A specimen was caught, hauled, preserved, carried, and only then interpreted. In the bathysphere, perception and environment were brought close together again. What swam past the window was encountered in the medium where it lived, under pressure, in darkness, in the spatial uncertainty that shaped its being. Even though the observer remained enclosed and dependent, the world outside was no longer arriving after the fact. It was present. Beebe's gifts as a writer became especially important here, because the meaning of the descent depended not only on seeing, but on describing what seeing in that setting was like. He had an eye for atmosphere without losing his grounding in natural history, and that combination helped him translate a fundamentally alien visual experience into language others could imagine. He described luminous creatures, changing layers of darkness, the strange clarity with which some forms appeared and vanished, and the way organisms that looked almost implausible in jars became coherent once encountered in their own medium. These were not merely aesthetic impressions. They were observations that restored to underwater life something long denied it by dredging and trawling. Context. That restoration changed the meaning of marine evidence. A fish or jelly-like form seen alive behaves differently from a specimen pinned into taxonomic significance. It occupies space. It moves with purpose or drift. It may generate light, hold its body in a particular way, or appear ghost-like, not because it is poorly preserved, but because transparency is one of its living adaptations. Beebe could watch relationships between body and darkness that no museum drawer could capture. He could notice how a beam of light altered the scene, how some creatures flashed and others receded, how the lower waters were not inert, but full of events calibrated to conditions radically unlike those at the surface. The hidden realm began, at last, to behave before human eyes. This did not mean that everything seen through the bathysphere could be settled beyond dispute. Observation through a small window in a narrow cone of artificial light is still a constrained form of seeing. Distances are hard to judge. Creatures may appear only briefly. Some identifications were later debated, and Beebe's descriptions for all their care, depended on the interpretive skill of an observer working under unusual conditions. That should not diminish the achievement. If anything, it locates it more precisely. The bathysphere did not abolish mediation. It replaced one form of mediation with another, and a far richer one. Instead of studying a world only through what had survived being torn out of it, scientists could now study it through sight that remained inside the environment. However briefly and imperfectly, the descent records from Bermuda also made another point newly tangible. The lower waters were layered in ways earlier sampling had only partly suggested. As the sphere sank, it passed through changing zones of life and changing relationships to light. Near the top, the world still belonged partly to the sun. Farther down, bioluminescence and the bathysphere's own lamps reshaped perception. What had once been imagined as a single downward fall into absence now seemed more varied, more structured, more ecological. Vertical distribution was no longer merely a matter of plotting where specimens had been recovered. It could now be experienced as a gradual change in visual and biological atmosphere. By 1934, Beebe and Barton had reached a depth of 3,028 feet, a record for human descent at the time, and one of the most famous milestones in underwater history. Yet the number, for all its symbolic power, is not the deepest meaning of the story. More important is what that descent represented in the evolution of attention. A place long known through delay had become, for a few moments, contemporaneous with observation. The lower world was still remote, still hostile to ordinary presence, but it no longer belonged entirely to inference. Human sight had entered it. It also entered public imagination. Beebe was one of those rare scientists whose observations could travel beyond specialists without being reduced to mere spectacle. His books and reports helped make underwater descent part of a broader fascination with exploration in the early 20th century. Yet his writing did more than entertain. It invited readers to understand that the world below was not simply a repository of odd creatures. It was a habitat with its own logic, and its inhabitants made better sense when seen as participants in that logic. In this way, Beebe helped pull marine science away from the old cabinet of curiosities view of strange organisms and toward a more ecological sensibility. One can also see, in Beebe's temperament, a subtle resistance to the dismembering habits of earlier natural history. He was fully a scientist of his time, but he was drawn to wholeness of experience. That may be why the bathysphere story continues to resonate. It marks the moment when a hidden environment stopped being merely an assemblage of retrieved parts and became, however briefly, a scene. The observer was still separated by steel and quartz, still dependent on surface machinery, still limited to a tiny field of view. Even so, the encounter had crossed an important threshold. Knowledge now included presence. At the same time, the limitations of presence were becoming newly visible. The bathysphere could go down only where supported from above. It could not roam across vast distances. It offered glimpses, not surveys. It opened a window into one kind of truth while leaving many others unresolved. How extensive were the structures below? What was the larger shape of the hidden terrain across whole basins and ridges? How could one connect local sight to planetary pattern? The sphere gave marine science a human eye in darkness. But one eye in one small chamber could not by itself reveal the architecture of the world beneath the water column. That point matters because the history of discovery rarely settles in one mode for long. Once direct sight becomes possible, it sharpens the appetite for broader vision. Beebe and Barton showed that life at depth could be encountered alive, in its own suspended world. And that changed the very texture of what marine science could mean. Elsewhere, though, other investigators were developing tools that would extend human perception in a different direction. Acoustics, echo sounding, and later, wartime technologies would transform not the intimate scene outside a small window, but the vast hidden contours of the planet below. Human beings had learned, at last, to look downward with their own eyes. The next revelation would come when they learned how to listen outward across the dark and turn sound into structure. And once human beings had begun to look downward with their own eyes, another desire grew beside that first triumph. A glimpse through a small quartz window could restore life and atmosphere to the lower waters, but it could not reveal the larger shape of the planet beneath them. It could not tell where ridges ran for thousands of miles, where trenches folded downward, where broad rises interrupted the great basins, or how the hidden terrain connected one oceanic region to another. The next transformation would come through a different kind of perception altogether. Instead of lowering a person into darkness and waiting for forms to drift past, investigators would learn to send sound outward, receive its return, and turn echo into geography. There is something beautifully strange about that shift. For centuries, the underwater world had resisted ordinary sight. Then, just as science began to reclaim a little direct vision through descent, it discovered that the most powerful way to grasp the larger architecture below was not by seeing in any familiar sense, but by listening. A pulse of sound sent downward could travel through water, strike the bottom, and return. The elapsed time could then be converted into depth. What had once required immense labor with line and weight could now be surveyed more quickly and over far greater distances. The darkness below would start to answer acoustically. The foundations of that acoustic turn lay in a mixture of accident, loss, engineering, and war. The sinking of the Titanic in 1912 helped intensify interest in underwater detection, especially in public imagination, though the technologies that matured afterward were driven by several forces at once. During and after the First World War, research in acoustics and echo sounding developed rapidly. Signals sent through water might reveal obstacles, submarines, or bottom depth. Military need sharpened technical ambition, as it so often does. But the scientific consequences would reach much farther than naval defense. Once sound could be used to measure depth at speed, the underwater world could begin to emerge not as isolated stations on a chart, but as continuous form. That continuity mattered enormously. Earlier generations of naturalists and surveyors had worked point by point. Sounding here. A dredge there. A recovered sediment or temperature measurement somewhere else. From such fragments, they built the first serious pictures of what lay below. But a planet-sized terrain cannot fully appear through scattered punctures alone. It needs lines, transects, repeated crossings, enough data to show whether a rise continues, whether a basin broadens, whether an underwater mountain chain is local accident or global system. Echo sounding opened precisely that possibility. It did not abolish uncertainty, but it reduced one of the most stubborn limits in underwater science. The hidden floor could now be traced with a new kind of persistence. One of the great early demonstrations came from the German expedition of the Meteor between 1925 and 1927. The Meteor crossed the South Atlantic repeatedly, using echo sounding to gather an unprecedented quantity of depth measurements. This was not an expedition of dramatic descent or biological spectacle. its power lay in repetition, coverage, and methodical accumulation, line after line, sounding after sounding. The hidden terrain began to appear less like a few isolated facts and more like connected topography. What emerged was a much clearer picture of the Mid-Atlantic Ridge as a major continuous feature running down the center of the basin. That ridge had not been wholly unknown before. Earlier soundings and inferences had already hinted at elevated structures beneath the Atlantic. But the meteor helped make the feature harder to dismiss as a scattered irregularity. A continuous rise of that scale demanded a different kind of thought. The ocean basin was not merely a receptacle bordered by continents and filled with water. It had great internal architecture. Something immense ran through it. And yet even then, the full meaning of that structure was not obvious. To discover shape is one thing. To understand what shape means in planetary terms is another. Meanwhile, acoustics was producing another surprise. One that revealed how a new instrument could both illuminate and mislead. During the Second World War, sonar operators sometimes detected what seemed like an underwater boundary, a false bottom suspended above the actual seafloor. Stranger still, this boundary appeared to move. It rose toward the surface at night and sank again by day. The phenomenon would later become known as the deep scattering layer. What the instruments had intercepted was not geology at all, but dense layers of animals, especially fish and zooplankton, whose bodies reflected sound strongly enough to mimic the return from a solid boundary. This episode belongs here because it captures the deep ocean's double character during the age of acoustics. On the one hand, sound made the lower world more available than ever before. On the other, that very availability produced new illusions. Investigators had not merely found a better map-making tool. They had entered another layer of indirect knowledge, one in which biological masses could masquerade as structure and interpretation remained as important as instrumentation. The underwater world was still capable of resisting simple reading. Yet even that resistance was productive. The deep scattering layer eventually became evidence of large daily vertical migrations by marine organisms, one of the most extensive synchronized movements of life on Earth. A false bottom turned into a biological revelation. So the acoustic era did something subtle and important. It did not replace earlier marine science. It braided together physical structure and living process more tightly than before. Sound traced the bottom, but it also bounced from moving life in the water column. The lower realm was beginning to reveal itself as an interlocked system of terrain, circulation, and biology. Still, the largest conceptual revolution would come when those lines of sounding were brought into conversation with a patient, visually disciplined form of map-making. That is where Marie Tharp enters the story. Tharp had studied geology and mathematics and began working in the mid-20th century at what would become the Lamont Geological Observatory. The setting in which she worked was shaped by both opportunity and exclusion. She was capable, precise, and unusually adept at seeing pattern in large sets of spatial data. Yet she belonged to a scientific culture in which women were often barred from shipboard research or relegated to supporting roles. She could analyze data, draft maps, and interpret profiles, but much of the direct fieldwork at sea remained socially closed to her. In one of the quiet ironies of scientific history, the exclusion that kept her from research vessels also concentrated her attention where she would make one of the most important interpretive breakthroughs in 20th century Earth science, working with Bruce Heezen, who led marine geological projects and spent far more time at sea. Tharp began compiling bathymetric profiles from echo-sounding data gathered across the Atlantic. Her work demanded patience of a special kind. This was not the drama of descent or the excitement of a strange specimen hauled from darkness. It was long, exacting labor with paper, profiles, depth readings, and cross-sections. She drew and compared, looking for continuity where others might have seen only isolated lines. Such work requires a rare cognitive skill, the ability to translate countless local measurements into coherent spatial imagination. One does not merely record, one sees through accumulation. As Tharp plotted the mid-Atlantic ridge, she noticed something striking. Running along the crest of the ridge was a central valley, a rift-like depression. It did not look like a random wrinkle or a cartographic accident. It looked structural, as though the ridge were being pulled apart or opened along its axis. This was profoundly suggestive, because by the mid-20th century, Alfred Wegener's older theory of continental drift had not yet been widely accepted among geologists in the English-speaking world. Many found drift too speculative, too lacking in mechanism, too disruptive to established views of a more fixed crust. A rift valley down the middle of a vast submarine ridge seemed to imply movement, tension, and a planet more dynamic than many experts were comfortable admitting. Here, the human dimension of discovery becomes especially visible. Heezen reportedly dismissed Tharp's interpretation at first as girl talk, a phrase that has endured because it captures so much in so little. It captures gendered condescension, certainly, but also the broader scientific resistance to implications that felt too large, too disruptive, or too close to a disfavored idea. Tharp's Ridge Valley was not simply a new feature on a map. It threatened to reorganize how the solid Earth itself was imagined. Her insight did not meet only evidentiary scrutiny. It met the social and intellectual inertia that often protects existing frameworks from uncomfortable revision. What makes Tharp so compelling is the nature of the evidence she trusted. She did not have a single spectacular observation forcing instant conversion. She had consistency. Profile after profile suggested the same structure. The shape kept returning. In science, repetition can be more powerful than drama, especially when the repetition is spatial. A pattern that reappears across independent lines of data begins to acquire the force of reality before the culture around it is ready to admit what it means. Tharp held to the pattern because she could see it in the compiled form of the data. And that kind of seeing is its own virtue. It depends on restraint, patience, and confidence in careful geometry. The case strengthened when earthquake data were compared with the maps. Seismic activity lined up along the ridge system in ways that made the Central Valley still harder to dismiss as coincidence. If earthquakes were clustering there, then the structure was not merely topographic. It was active. The underwater world beneath the Atlantic had ceased to look like an old, static basin with a few irregularities. It now suggested a great planetary seam, part of a crust in motion. The seafloor began to seem alive in a geological sense, as something being made, broken, and reshaped. This was a radical change in human understanding. For a long time, the underwater realm had entered scientific thought mainly as a biological question or a surveying challenge. Could life exist there? What was the depth? What sediments covered the bottom? Where might a cable lie? Even when large expeditions like Challenger transformed the scale of inquiry, the hidden terrain was still often treated as a setting for marine processes, rather than a dynamic participant in Earth history. Tharp's maps, together with the growing body of marine geophysical evidence, pushed beyond that older frame. The Atlantic floor was not simply where things were found. It was part of how the planet worked. The phrase seafloor spreading would emerge from this broader mid-century revolution, especially through the work of Harry Hess and Robert Dietz, who argued that new crust was created at mid-ocean ridges and moved outward. Those theoretical developments belong to a wider story. But within this one, their significance is clear. The ridges and rifts mapped through soundings and profiles had become evidence for a mobile Earth. Continents were no longer to be imagined as fixed blocks above passive ocean basins. The crustal surface itself was implicated in a system of creation, motion, and destruction. Much of the decisive evidence came from the terrain beneath the oceans, a place humans had only recently begun to map with any seriousness at all. There is a deep irony in that. For centuries, continents had dominated imagination because they were where human life unfolded, visibly. Yet the clues to one of the 20th century's greatest revolutions in geology were hidden under the waters between them. The Atlantic, once imagined mainly as a corridor across which ships moved, had become a text about the Earth's interior processes, and that text had been read partly through technology born of war, partly through the patience of acoustic surveying, and partly through the interpretive discipline of a woman who was not allowed to go to sea as freely as the men whose data she transformed. Tharp's later physiographic maps did more than convince specialists. They gave the public and the broader scientific community an image of the submarine landscape that could actually be pictured. One of the difficulties of underwater science had always been its abstraction. Numbers, profiles, and isolated soundings are cognitively demanding. A sweeping map, by contrast, can shift intuition almost at once. Ridges, trenches, fracture zones, and basins become imaginable. The hidden surface of the planet develops relief in the mind. In that sense, Tharp did not merely analyze data. She altered planetary imagination. And still, the lower world preserved its power to surprise. Acoustic systems that revealed ridges had also revealed migrating biological layers. Maps that clarified structure also raised new questions about volcanism, heat flow, earthquakes, and crustal renewal. The ocean floor was becoming legible as a vast dynamic system. But its dynamism pointed outward into new mysteries rather than toward closure. If the ridges marked places where the Earth was actively generating new crust, then what other unexpected conditions might exist along those great submarine systems? What chemistries, temperatures, or biological possibilities might cluster around them? Human beings had learned to hear the hidden terrain and map its architecture. The next surprise would come when they reached one of those active zones directly and found that the darkness there was doing far more than shaping rock. And so, the hidden ridges and rifted seams of the planet began to draw human beings downward, once again. Once the lower world had become legible as a dynamic geological structure, it was no longer enough to know that the seafloor had shape. People wanted to reach the most extreme places it contained, test the limits of descent itself, and see whether the structures revealed by sound and mapping might also conceal conditions no one had imagined. The old questions about darkness, pressure, and life had not disappeared. They had returned in a more demanding form. If the planet was making crust in the darkness below, if its submerged mountains and trenches were active rather than inert, then what else might be happening there, beyond the reach of ordinary intuition? One symbolic answer came in January 1960 at the Tientvers, when Jacques Picard and Don Walsh descended in the bathyscaphe Trieste to the Challenger Deep, the deepest known point in the world's oceans. The craft belonged to a new phase in underwater engineering. Unlike the tethered bathysphere, the bathyscaphe was designed for freer vertical movement, using a float filled with gasoline for buoyancy and a pressure sphere hanging beneath for the crew. It was an apparatus shaped by physics in the most literal sense. Every aspect of its form acknowledged pressure, density, and the vast difference between the human body and the environment it hoped to enter. To descend in such a vessel was not simply to travel downward. It was to entrust one's life to a mechanical shell, carrying human attention into a place evolution had never prepared the species to inhabit. The descent has often been remembered in simplified heroic form, as though the deepest point were merely waiting to be reached and then checked off like a summit. From inside the story, it feels more fragile than that. Only weeks before the record dive, a component associated with the pressure sphere's outer window system had cracked during another deep descent. A reminder that the materials separating observer from catastrophe were always under extraordinary strain. The final dive succeeded, but the success retained the atmosphere of contingency that belongs to so much underwater science. The lower world had never offered entry on generous terms. Even in 1960, with all the advances since sounding lines and dredges, reaching the bottom of the Mariana Trench meant entering an environment where any failure of seal, sphere, or system would be decisive. When Trieste settled onto the bottom, the achievement was immense in human terms. Yet the scientific meaning of the moment is subtler than the record alone suggests. The floor of Challenger Deep did not open itself into clarity simply because two men arrived there. Sediment was stirred. Visibility was limited. Time was short. The observers reported what they could under conditions that remained constrained and unusual. One of the most discussed details from the dive was the reported sighting of a flatfish-like creature. Later scientists questioned whether such an animal could plausibly have been a true fish at that depth, and some suggested that what was seen may have been another type of organism, perhaps a sea cucumber or something else misinterpreted in poor viewing conditions. That ambiguity is worth preserving rather than smoothing away, because it tells the truth about the history better than a cleaner story would. Even at the greatest depth yet reached by human beings, certainty did not arrive whole. There is something almost poetic in that. Humanity had reached the bottom of the known oceanic world, and still the place refused to become simple. The dive proved that people could get there alive. It proved that the trench floor was not beyond all possible human contact. But it also proved that presence alone does not eliminate interpretation. The oldest pattern in the history of deep ocean discovery remained intact. Every time humans found a way to push farther into darkness, the darkness answered with more complexity rather than final resolution. And yet Trieste mattered profoundly. The dive compressed centuries of effort into one almost unimaginable act of descent. Lines, dredges, sounding machines, charts, acoustic surveys, bathysphere glimpses. All of it led, in some sense, to that steel sphere arriving in the Hadal depths. It made the planet's most remote marine depression a human place in the narrowest but most literal sense. Someone had been there. Someone had looked. The trench was no longer purely inferential. In intellectual history, such moments matter even when the direct observations are sparse, because they alter what the mind considers reachable. A region once treated as absolute remoteness enters the field of possible encounter. Still, The next great revelation would not come from the deepest point. It would come from a different part of the underwater world entirely, and from a question that at first seemed almost unrelated to biology. If the long mid-ocean ridges mapped in the 20th century marked sites of crustal activity, then geologists and marine scientists wanted to inspect them more closely. A place where the Earth appeared to be generating new crust might reveal heat flow, volcanic processes, and chemical exchanges between rock and water. The interest was geological first, or at least heavily geological. But that, too, fits the larger pattern. Again and again, the lower world was entered for one reason and found to contain another. This is where Alvin enters the story. Commissioned in the 1960s and developed at Woods Hole Oceanographic Institution, Alvin was a small, maneuverable deep submergence vehicle built for scientific work. It did not merely drop straight down and return. It could move across the bottom, carry observers to specific sites, and support repeated investigation of features that acoustic surveys had already indicated but could not fully explain. If the bathysphere had brought the first sustained human eyes into the deeper water column, Alvin represented a further maturation of underwater science. It made targeted, revisitable descent more practical. The observer was no longer only a witness to whatever drifted past a small stationary sphere. Now the observer could begin to investigate place. That change in mobility mattered because it linked two kinds of knowledge that had previously remained partly separate. Acoustic mapping could reveal large-scale structure. Direct descent could restore local reality. Alvin helped join the two. Scientists could now aim for features suggested by maps and profiles, then inspect them with their own eyes. Instruments and cameras. The underwater world was becoming navigable in a new sense. Not easy, not transparent, not fully familiar, but increasingly susceptible to planned visitation. This altered the pace of discovery, because one could begin to ask not only what lay below, but what lay at a specific underwater ridge, fracture zone, or volcanic site. In the 1970s, that possibility led toward one of the most important turning points in the entire history of marine science. Investigators working near the Galapagos Rift had reason to think that something geologically interesting might be happening there. Heat flow measurements and seafloor spreading theory had already made mid-ocean ridges central to Earth science. What remained uncertain was the exact character of the environments along them. To help search for active venting, scientists used a deep-towed camera sled called Angus, which could photograph sections of the seafloor in detail. In 1977, imagery from this search revealed something unexpected. Clusters of large organisms associated with areas where warm, chemically altered water appeared to be emerging from the crust. The surprise was immediate, though its full meaning took time to register. The expedition that first identified the hydrothermal vent field did not even include biologists, a detail so strange and revealing that it seems almost designed to illustrate how discovery actually works. The researchers were not setting out with a dramatic theory that the lower world might host rich ecosystems supported by chemical energy. They were following geological questions. Yet on the seafloor appeared dense communities of life gathered around warm venting fluids in an environment far below the reach of sunlight. It was one of those moments when a long scientific story suddenly turns and reveals that one of its oldest assumptions has been incomplete in a deeper way than anyone had realized. To feel the force of this, it helps to remember how much of biology had long been structured around sunlight. At the surface and on land, the logic seemed universal enough. Photosynthesis captured solar energy. Plants and phytoplankton formed the base of food webs, and animal life depended directly or indirectly on that energetic foundation. Even once scientists accepted that animals could live far below sunlight, those animals were generally understood as relying, in one form or another, on organic matter, ultimately produced above and sinking downward. The lower world could be inhabited, yes, but it was still thought to belong energetically to the sunlit world. Hydrothermal vent communities disrupted that picture with astonishing force. Around vent sites, microbes were found to derive energy from chemical compounds, especially hydrogen sulfide, through chemosynthesis rather than photosynthesis. In plain terms, life in these ecosystems was not waiting for sunlight-derived food to drift down from above. It was anchored to chemical energy released by the Earth itself. Giant tube worms, clams, mussels, crabs, and dense microbial communities flourished around places where superheated, mineral-rich fluids emerged from the seafloor. The biological world and the geological world, which earlier science had often approached separately, were suddenly joined in intimate fashion. The Earth was not merely shaping habitat there, it was feeding it. This was the largest intellectual reversal since the collapse of the azoic hypothesis, and in some ways even larger. The older belief had held that life could not endure under the conditions of darkness, cold, and pressure found in the lower world. Later work showed that life did persist there. Hydrothermal vents went further. They suggested that an entire mode of living could be organized without direct dependence on sunlight. That did not merely enlarge the range of known marine life. It enlarged the human definition of a habitable world. If life could thrive around chemical energy from the Earth's interior, then the conditions required for complex ecosystems were broader than many had assumed. Questions about habitability could no longer be confined so narrowly to sunlight and temperate surfaces. And once again, the underwater world had corrected human thought by refusing an assumption that once felt natural. In 1979, scientists also identified what became known as black smokers, hydrothermal vents emitting dark plumes rich in metal sulfides. The name is vivid, but the deeper significance lies in what the plumes represented. Here were active exchanges between rocky crust and surrounding seawater, building chimneys, altering chemistry, and supporting dense communities of organisms. These were not static curiosities. They were ongoing processes, combining heat, mineral precipitation, microbial metabolism, and animal life in settings no earlier naturalists could have imagined from a ship's deck. The lower world had become not just a place of survival, nor merely a place of hidden structure, but a place of production and transformation. The psychological effect of this discovery on science was far-reaching. Hydrothermal vent communities challenged the old habit of treating darkness mainly as a condition of loss. Darkness might mean no sunlight, but it did not mean no energy, no structure, no abundance, no ecological sophistication. In fact, in some parts of the deep ocean, darkness coexisted with extraordinary productivity generated by geochemical processes. This changed marine biology, microbiology, earth science, and astrobiological speculation as well. Once one sees that life can organize itself around chemistry emerging from rock and water, the imagination begins to travel. It travels to early Earth. It travels to icy moons. It travels to any world where liquid water, energy gradients, and the right chemistry might meet. The deep sea on Earth became a laboratory for thinking beyond Earth. Yet even this revelation did not close the story. If anything, it made the remaining unknowns feel larger. Hydrothermal vents were found at some ridge systems, then at more. Cold seeps and other chemosynthesis-based communities expanded the sense that the lower world held multiple pathways for life. Better submersibles, remotely operated vehicles, and seafloor observatories increased the pace of observation. High-resolution mapping improved. Cameras, sensors, and sample systems became more sophisticated. And still, much of the ocean floor remained only partially known in detail, especially when compared with the intimacy of knowledge humans possess of landscapes on land. The paradox persisted. The largest living space on Earth had been transformed by science, but not exhausted by it. That unfinished quality is the most honest way to end the journey. Human beings learned to lower lines into darkness, to draw the first hidden contours beneath the Atlantic, to argue over whether life could survive in cold and pressure, to launch global expeditions, to be fooled by artifacts and by their own desire for neat conclusions, to descend inside steel spheres, to map ridges and trenches with sound, to discover that the crust below the oceans was active, and then to find entire ecosystems flourishing without sunlight. Each step felt, for a moment, like a threshold, and each threshold opened into another region of uncertainty. So when we speak of how humans discovered the deep ocean, the phrase is both true and incomplete. We did discover it, in the sense that we learned enough to transform it from blankness into a structured, inhabited, dynamic part of the Earth. But we also discovered again and again that the lower world does not yield to one final act of understanding. It remains a place where tools mediate perception, where scale defeats intuition, where whole forms of life can remain hidden for centuries, and where even the best maps still stand for only part of what is there, beneath the roots of ships, beneath weather and light, beneath the daily life of the surface world. The planet is still thinking in darkness. Heat rises through cracked crust. Mineral plumes gather. Creatures move through pressures humans can scarcely imagine. Vast areas remain imperfectly mapped, sparsely visited, or known mostly through remote instruments and partial surveys. The deep ocean is no longer the empty underside imagined by earlier centuries. But neither has it become ordinary. It remains, even now, a place that humbles explanation. Perhaps that is the final lesson it offers. Discovery is not always the replacement of mystery with mastery. Sometimes it is the replacement of one small mystery with a larger and more accurate one. The hidden world below the sunlit surface has entered human knowledge, yet it still preserves the power to revise what humans think life is, where life belongs, and how much of their own planet they have truly learned to see. By the end of this story, the deep ocean no longer feels like a blank space beneath the familiar world. It becomes something far more profound, a hidden realm that forced human thought to change shape in order to meet it. The abyss was measured before it was understood, sampled before it was seen, and explained many times before those explanations could survive the weight of better evidence. In that sense, the discovery of the deep ocean was never only about water, depth, or strange creatures. It was also about the discipline of letting reality correct the mind. What changed was larger than marine science alone. As the deep sea slowly came into view, it altered the human picture of life, of Earth, and of the conditions under which living things can endure. It weakened the old habit of assuming that what seems impossible to us must be impossible in nature. It revealed that darkness is not emptiness, that pressure does not guarantee silence, and that a place can remain physically present for all of human history while still being, in intellectual terms, undiscovered. The deep ocean taught science a kind of patience, and perhaps a kind of humility as well. That may be the most enduring meaning of the journey. Curiosity is often imagined as a bright, confident force, but in practice it is just as often slow, doubtful, and shaped by error. People lower lines into darkness, build instruments that only partly work, misread what they find, begin again, and slowly learn how to ask better questions. And even now, with all that has been mapped and recorded, the deep remains unfinished in human knowledge, somewhere below the surface, beyond the range of ordinary sight. The planet is still keeping part of its reality to itself, waiting for the next patient question.